cloud. So when you want.
Okay, I'll share my screen right now. So we can begin. So good afternoon, everyone. My name is Juan Manuel Munoz. I am professor at the Mechanical Engineering Department at Madrid Technical University, UPM, in Spain. And in this class, I would like to make an example to show you how to use CAE tools while developing a product. CAE stands for Computer-Aided Engineering, and it's a set of powerful tools in order to help you doing design and doing virtual testing and doing other stuff that I'm going to explain shortly. I will make an example how to design a surgical tool. That's very easy with an easy geometry to show you the different functionalities and the potential of these tools for helping you in the design. Okay. So first of all, I would like to just to describe where CAE tools are used, why they are used. This is an overview of the complete development process of a product. Andres, Carmelo, Licia, I think you have had some classes regarding how to manage the development of a biomedical product. So this is the general pattern of any product for developing any product, no matter if it is a biomedical device or it is a financial product. So the development process is more or less the same always. First of all, you have to detect a need, as you are doing right now in the bootcamp. You are detecting a need, and you're trying to find ideas for fulfilling that need that are technically and economically feasible, okay? Once you have ideas that are promising, that are feasible in financial, economical, and technical terms, you begin finding or trying to find solutions, technical solutions, in order to materialize this idea in a tangible product or even in an intangible product, for instance, when it is a financial product or it is a software. But you need also to find different possible concepts in order to be able to fulfill all the required functionalities in a timely, costly, and technically feasible manner. Afterwards, you begin with the design itself, with the detailed design itself, where you try to fit and to match many different partial solutions and combine them in a global solution that fills the functionalities. And finally, you have to operate the product. So you have to introduce the product in the market and manage all the life cycle of the product in the market. That it is very difficult also because you have warranty problems, you have cost reduction activities, you have production site changes, you have many different things that can happen during the product life in the market, and you have to manage. CAE tools are basically used in the design itself, from the design activities themselves, and also during the life cycle of the product. For instance, imagine that you have to do a lot of testing with different prototypes in the product. Imagine you have to do crash tests in a car. So you can imagine that the tests are really expensive and they are really time consuming because you need a lot of time to be able to manufacture a prototype that is realistic and has all the functionalities you pretend your final product to have. And it is a really expensive activity. The cost of a product can be very easily 100 times, 10 times bigger than the cost of the product when it is in serious production. So testing is a really expensive and costly and time-consuming activity. So if we could make virtual testing before doing the actual prototype, the final prototype, we would save a lot of cost and a lot of time. So CAE tools are very appropriate for that because you can make realistic simulations. You can try different solutions and measure the impact of each solution in the final product without making a physical prototype. Okay. Also, during the concept design or in the embodiment design, it's called basic engineering, you can also check whether or not the different components that are going to be installed in the global part will fit each other. Or you will have interferences, you will have tolerance problems when you combine hundreds of different tolerances of different components. The overall tolerance is very difficult to calculate. You can also make such kind of analysis with a CAE program. during the market implementation and market life of the product, you can also use CAE programs to help you managing all the product documentation, all the design changes, how to implement the design changes in the different stakeholders, so intermediate warehouses, final customer stores, technical services, factories, etc. So it's also very important to have a CAE program embedded in the enterprise resources management program so that you can do all this stuff. Okay, so CAE programs are really used in almost 100% of the companies due to the cost and time savings that they allow to get. Okay, so these are just, I have listed here some functionalities related to the technical development of the product, but also related to the product life during the market. Okay, so as you know, we can make a structural analysis of different kinds: linear, non-linear analysis, buckling, vibration analysis, crash analysis, thermal expansion, thermal differential expansion studies, fluidic analysis. For instance, in a biomedical device, fluidic analysis are very important because small pressure differences can be very, very harmful for the patient, as you know. And you can also calculate, for instance, pressure losses in order to be able to determine the power needed in a pump, etc. So the turbulences in certain geometry with certain material characteristics. So it is very, very powerful. The CFD, the computational fluid dynamic analysis that can be done by means of CAE programs. You can also do couplet fit analysis. That means, for instance, imagine that you have to design a combustion chamber, or imagine you have to design in the biomedical engineering field. Imagine you have to design a mixture chamber inside a bigger system related to the infusion pump, for instance, or anesthesia pump. You need to combine different fields. For instance, you need to combine fluidic and chemical field, fluidic and thermal field, thermal and structural field, fluidic and structural field. So you can do very complex analysis with a very high accuracy, especially in the last years due to the power of recent computers. The accuracy you can achieve with the CAE program is really high. So we are in Industry 4.0. We are moving from virtual prototypes even for digital twins. So the degree of accuracy, the level of complexity of the models we can simulate with a CAE program is so high that we can almost in real time be able to reproduce the behavior of a product, even when the product is already in the market. Okay? Even we can simulate the behavior in advance. So we can predict what is going to happen to the product. So that allows us to establish countermeasures related to failures, to plan different predictive maintenance activities. So these are really powerful help we can achieve from the CAE programs in the framework of Industry 4.0 with regard to the digital tool. Okay, so I'm going to make a very simple example with a CATIA program. You know, there are different CAE packages. I think I have listed here the most famous one. I am sure you know many of them. For instance, CATIA is traditionally used in the aeronautics sector. NX is also used in the industry. HyperWorks is used also in the aeronautics sector and automotive sector. And Inventor and SolidWorks are more used in the academic environment. So perhaps you are familiar with one of these programs. And these programs are integrating packages that, among others, have finite element packages, as ANSYS, Nastran, or LS-DYNA, that are very powerful simulation tools that have been implemented since many years. For instance, Nastran was created by NASA about 40 years ago. So the program is very well developed and debugged. So it is really powerful. I'm going to make an example with CATIA. It's a very simple example. We will try to analyze, we will try to design the shape, the thickness, the curvatures, and the materials of this part. This part is just one part of a bigger system. This is a separator used in thoracic surgery. And we're going just to model one of the parts, so this part. what I'm going to do is creating a surface, and then take this surface as a basis. I'm going to make a structural analysis using approximate boundary condition and approximate forces that can reproduce more or less the forces this device is going to withstand when in operation. Okay, so what I'm going to do first is creating the geometry. Sorry. Creating the geometry, I'm going to create a spine in CATIA. So I'm going to try to create a line that is something like this. And on this spine, I'm going to create some intermediate sections of the surface. So I will create a curved section here. I will create a straight section here and here, so that I can interpolate a surface, having the surface cross sections that are controlled by the intermediate lines I have drawn. So you will see we have a surface with a variable curvature. Okay. Any of you know why we need a curvature here? You can answer if you want in the chat screen of the Zoom. Yeah, but try to imagine, why do we need a curvature here, and why do we need this shape? Why do we need this this splitting here, this hole in the system? Because we are going to try to optimize the design, or to take into account different things related to the geometry and thickness and material of this part. Okay, so I'm going to change to the CATIA screen. So give me a second. Okay, can you see the CATIA screen?
Sí.
Okay, thank you. Okay, so first of all, I'm going to create the spine. I'm going to create a new. Okay, let's name this part. And what I'm going to do is go into the surface module. Okay, you see CATIA has different modules, many different modules, so that you can do different kinds of operations. For instance, creating solid parts, creating surfaces, doing structural analysis, but it's going to do later, or try to create all the trajectories needed for the CNC machine to manufacture one part we have already designed, doing kinematic checks, thermal checks, etc. So I'm going to open the surface module so that I can, okay, I'm ready in the surface module, okay. So I can design the surface. First of all, I will do a sketch. So you can imagine, if I want to draw a curve, I need a piece of paper where I can draw it. I need a 2D paper. So what I am going to do is specifying which plane I'm going to use for drawing. I am already in a 2D environment. So I will draw the spine, okay, by means of several straight lines, okay? So I will set the length of this line, for instance, in, let's see, 60 millimeter. Then I'm going to draw a horizontal line of, let's see, 90 millimeters, for instance. Okay. 90 millimeters. And then I'm going to do the curved part you saw here on the tip of the tool. Okay, so that I'm going to draw an auxiliary line. Okay, I'm going to make this line auxiliary. So you see the line is not continuous anymore, it is dashed. And I'm going to force this line to be coincident with the end point of the spine. Okay, sorry. Okay, with this menu of restraints, I can force the line and the point to coincide. Okay. And then I will draw a circle that I will cut later. I will force the circle, sorry. I will force the circle to be tangent to the line, and I also be forcing the center of the circle to be part of the auxiliary line so that I can locate the circle exactly where I want to be. Okay. I'm going to force it to be tangent to this line. Okay. And I will set the circle diameter. For instance, I don't know, perhaps 20 millimeters is okay. And then I'm going to draw another auxiliary line so that I can cut the circle as I want to cut it. Okay. I set the angle between these two lines to be, for instance, I don't know, 30 degrees. Okay, and then I'm going to trim by means of this eraser. I'm going to trim perhaps 30 degrees is, that's 60 degrees is okay. Okay. I'm going to erase the part of the circle I don't need, okay? Okay. And now I'm going to fillet this corner. You know, in mechanical engineering, corners are the enemies of the mechanical engineers because they create a lot of stress concentrators. So we need to create parts that have as less corners as possible. So I will try to fillet this corner so that I don't have problems later, okay? Okay. And I will define also the fillet radius to be, for instance, 20 millimeters. Okay, so I have the spine already. Let's go to the 3D environment again. And let's try to define the intermediate sections that will be later connected to form the surface, okay? I will try to create a curve here. So I need a plane, I need a 2D plane here so that I can I can draw the curve on it. So I'm going to define an auxiliary plane, which is parallel, for instance, which is parallel to this one, located at this point, okay? I have the auxiliary plane already so that I can draw the line, I can draw the curve here. Okay, we are into the environment again. You see where we are drawing, okay? So what I'm going to do basically is to define the curve section of the tool here. So I will draw a circle and I will force the circle to pass through the sketch origin. And then I will cut the circle so that I can have the cross section I want to have. Okay, I will make this line as auxiliary. Sorry. Okay. And I will cut the circumference. And then I will define the distance between this line, for instance, and the horizontal axis of the sketch. Let's define 5 millimeters. And I will also try to establish the distance between the endpoints of the circular section. Okay, this one and this one. Oh. Okay. For instance, 20 millimeters. Okay. Then go back to the 3D. I will create an auxiliary plane here also so that I can draw a straight line, because from this point to the other tip of the tool, I want the section to be straight. So I will create another auxiliary plane parallel to that one through this point so that I can draw the line here. Okay. You see that I'm going to draw the line at this point. Okay. So just draw a straight line. 20 millimeters in length. And I will also define the distance between the sketch vertical axis and the end point of the line to 10 millimeters, so that this is symmetric. Okay. And finally, I will do the same at this point. Okay, I will do another straight line at this point so that I can have the 3 intermediate cross sections that will allow me to construct the surface. So I will create another auxiliary plane, a final auxiliary plane, which is normal to the curve. Okay, normal through this curve through this point. And I will do the final sketch here. Okay, I will do a horizontal line and I will force the line to be coincident to that end point of the spine. And I will set the line length to 20 millimeters and the distance of the end point of the line to the vertical axis of the sketch. Okay, so 10 millimeters also, so it is centered. Okay, so then I can construct a surface already. I'm going to no, I'm not going to delete so far. I will do it later. Okay, so let's use this command. So multi-section surface. Okay, so I will define the intermediate sections I want. And I will also define the spine. Okay. So I finally have the surface. Of course, it is a simplified surface. If you see the part I have showed you, the real surgery tool is a little bit more difficult. It has some cuts here. I will not do that cuts, but I will do the cut necessary to fix this part to the rest of the system. Okay. So I will draw a new sketch in this surface. To design the hole I'm going to have in the part to fix it. So I just set the length of the pocket. Let's see, 45 millimeters, for instance, or perhaps 50 millimeters is okay. The width, about 5 millimeters. I will position it so that it is symmetric. So I will define this length to be 1/2 of 5 millimeters, so that is 3.5. And as corners, no, let me position the whole pocket with respect to the sketch. Okay, so I will define the length between this line and the horizontal axis of the sketch, so that I can set this length to perhaps 25 millimeters. Okay, I think I can make this a little bit longer. And you know that corners are the enemies of mechanical engineers, so I will try to fillet these corners also. I'm going to hide the surface because perhaps you cannot see anything otherwise. Okay, so I fillet the corners. Okay, I will try to make a fillet of 2 millimeters in radius, for instance. On each corner of the pocket. I fillet this again. As you see, every operation I am doing in the model is being registered in this tree. So this is the specification tree. So this is very powerful because if I want to make some change in the prior stages, I can do it. So the change will be, all the effect of the change will be reverted to the rest of the model. Okay, then I fill it this finally. 2 millimeters. And finally, I will make the hole needed to introduce the screw that will fix this part to the rest of the system. So I will make circumference here. I will define circumference diameter, for instance, 10 millimeters, okay. And I will define, as you see the circumference is white, it is not green. It is because it is not fully constrained. You see I can move it, it is not fixed. So for having a green circumference, I have to define the distance between the center of the circumference, for instance, on the horizontal axis. Okay, let's see, 60 millimeter. And finally, I will delete the lines I don't need anymore. So these lines are not needed anymore. Okay. Then I will show the surface again. And I will make the pocket, okay? I can use the split command so that I can make the hole. Okay, and we can say that we have our geometry almost already defined. Yeah? Oh, sorry. Okay. Finally, let's define the material I'm going to use. In this case, I will select steel, stainless steel, of course, for this material. So I will assign the material to the surface. Okay. So the geometry is already defined, material is already defined. So I think we need to define the thickness. So for defining the thickness, what I will do is make a structural analysis to check the stresses and check whether or not stresses are too big or are acceptable, allowable for this design or for this material. Let me hide the auxiliary planes and also these ones, so that we just see the final surface, okay? And now let's go to the meshing module. So before making the structural analysis, I have to make a mesh. I have to discretize my domain. So I will try to make a good mesh. Okay, we'll use two-dimensional elements. And yes, I think 0.75 millimeters is a good mesh size, element size. Okay. Okay. Okay, mesh is already done, you see. I have discretized my whole surface in many, many different elements so that I can measure the stress and establish the structural analysis equations in each element so that we can combine them later. And once the meshing is done, we go to the structural analysis itself. Okay. I will define the thickness because I didn't define it yet. So I will tell the program that this mesh should have a 2 millimeter thickness, for instance. And then I'm going to define the boundary conditions. This part is fixed to the rest of the device by means of a screw and a nut, which is fastened here. So what I will do is creating like a clamping here. And for simulating the contact force between the tool and the patient for separating the flesh in order to the surgeon to operate correctly, I will just introduce a distributed force of 50 newtons, for instance, in this edge. which simulates the actual load when operating with the tool. And I think we can now make the simulation. So I will calculate. Okay, calculation is finished. So let's see the results. We'll see, for instance, the von Mises stress. Okay. Let's check the stress concentrators. You see, this is a corner. This is an enemy of mechanical engineers, right? So that's why the stress is too high at that point. The stress is about 900 megapascal. This is too much. I think this is not so important because this is a corner, and in the real life we don't have such a corner, so the stress will not be so high. This is a normal simplification that is done in infinite element analysis. So I think we should not be worried about this stress, but for instance, we should worry about this one. So it is about 325 megapascal. So this is allowable for a steel part, no problem. So the part will not break. We can also check, you see the part deformation. You see how the part will deform when subjected to this load. Okay? So the scale is almost 1-to-1. So I think the part is correctly designed. But now imagine that you want to make this part by means of a 3D printer, and the part, of course, must not be made of metal. There are metal 3D printers, but imagine that you don't have a metal 3D printer, that you have even if you have a metal 3D printer, this would be much more expensive than just folding a metal plate. So if you have a plastic metal printer and you want to make this part as a plastic part, let's see which is the thickness that we should have, because if we leave 2 millimeters, perhaps if the part is a plastic part, the stresses would be so high. Okay, so let's change the material and analyze what happened if I change the material from steel to plastic, okay? So I will change the material. Instead of metal, instead of stainless steel, I will select a material which is similar to the material that is used in the 3D printing processes, okay? Then I go back to my structural analysis module. Okay, and I just do the calculation again. Okay, let's see the results. Okay, you can see that the deformation is much bigger. So this is 1-to-1 scale, I think. No, this is not 1-to-1. This is less than 1-to-1. So the deformation will be even bigger, and the stresses will be very big for a plastic part. You see, for instance, the stress we have here is about 293 megapascal. So this is really big for a plastic part. Allowable stress in plastic is about 20 megapascal or even less than 20 megapascal. So the stress is really big. So what can we do? We can increase the thickness, for instance. Okay, so let's increase the thickness. For instance, let's define a thickness, instead of 2 millimeters, let's define 7 millimeters. Okay, let's do a thicker part and calculate again. Okay, let's check. And you see now the deformation is much smaller. Similar to the deformation we had in the metal part. and stressors let's see, are in the order of 25 megapascal. That is allowable, okay? When we get closer to the corner, the stresses will increase very quickly, but you see that the stress very close to the hole or to the corner is still allowable. So that means that we don't have to worry so much about this stress concentrate. Okay. So now perhaps we can decide that this is a correct design with increased thickness for a plastic part. So the last step would be to create an STL file so that we can transport the file to the 3D printer. Okay. So this is the last operation I will do. I will come back to the solid part. I will go to the part design module. And then I will give the real thickness to the part, okay? So let me look, okay. I will give thickness to this surface. So I will give a thickness of 3.5 millimeters from the surface to the outer part and 3.5 millimeters from the surface to the lower part, to the inner. Oh, what's the problem here? Oh, no. There's a problem here. I don't know what's the problem here. Let me check. That's right. Okay, yeah, okay. Okay. Okay, I have the 3D part already. And what I will do now is just go into the additive manufacturing module. Rapid prototyping. I will do the tessellation. So STL consists on a set of triangles that are sent to the 3D printer. So I will do the tessellation first. And I export this tessellation as an STL file, okay? So I will use this for the retractor. Okay, and that's all. Then I will take the STL file. I will save the STL file in a USB dangle, and I will connect the USB memory to the 3D printer so that they can, or to the slicer program, so that they can further finish the 3D printing. Okay, so that's all for the example. I hope you found the example interesting. I thought the example was good because it was simple enough to show you different functionalities of the program, and especially to show you how powerful the CAE program can be. You see, we have spent no more than 30, 40 minutes in order to make the complete material geometry analysis of a part. So I think you can take advantage of these programs in order to save a lot of money and a lot of time in the development of your products. Thank you very much.
Thank you, Juanma. Thank you very much. So are there any questions regarding this topic?
Yes, I'm Lucas.
Go, Lucas.
Maybe I just wanted to get a clarification because I can see the tool that Joan has used is quite powerful. Is it maybe superior to the other CAE packages like SolidWorks and Autodesk? I mean, in terms of the power, I mean, he has been quite fast in doing the design, modeling, and such, or is it because that he's an expert in the field and that's why he's been able to do all that within a very short time? And then number two, maybe will it take so much time for somebody maybe who knows Autodesk or AutoCAD to learn the is it called CATIA package that is used, so that maybe he can become quite well with the designs? Thank you.
Yeah, I think if you are used to AutoCAD, it is not difficult for you to learn how to use CATIA or NX. all the 3D based programs are the same in terms of usability. So the tools are the same, just the icons and some special parts of the procedure are different. But I think if you're familiar with your program, you don't have any problem learning a new one. It's really, really easy. I think you need, normal courses for geometry design in such a program are 25-hour courses. So it is a pretty short time.
Okay, thank you.
You're welcome.
I can simply add to this that some tools of Autodesk are free for students. So if you want to learn, you have the opportunity. And then I know that CATIA, or better Creo, is much more powerful where you have large assemblies. When you have like hundreds of parts, instead is, SolidWorks or Fusion are less effective with many parts. Can I ask you a question, Juanma? Is it possible to make like the analysis of contact?
Of course. If you have several parts in an assembly, you have to define all the interfaces between the parts. You tell the program how forces are transmitted between the parts. You can also define gaps or tightens or friction coefficients and so. And you can very accurately calculate the contact loads and the contact pressures arising between the parts.
Even if it is the same part which is collapsing.
I think CATIA is not able to do that, but for instance, NX is able to do it.
Okay.
We have used this feature, for instance, for designing spiral springs. A spiral spring can touch itself, for instance. So it is a difficult model, but NX can do it pretty easily and pretty accurately.
Okay.
And then, can I continue?
Yes.
Does CATIA have provision for electrical designs? Maybe because for some like SolidWorks, there's always SolidWorks for mechanical and SolidWorks for electrical. Does maybe the CATIA that you've used has that provision?
Yeah. CATIA allows you to design the geometrical part of electrical circuits, but it has no possibility of calculating the electrical parameters. So CATIA cannot make electrical simulations. I think NX and SolidWorks are able to do electrical calculations also. Yeah, but I am afraid that if you are using the electrical module of SolidWorks, perhaps your license doesn't allow you to use another module at the same time. So normally in the university license of SolidWorks, you can use just one package at the same time.
Okay.
So, thanks again, Juanma. Let me stop the
Pleasure.
recording. Stop recording.